Hey everybody, this video is for Chapter 5 of the Chemistry of Hazardous Materials class, and we will be taking a dive into organic chemistry by discussing hydrocarbons. Based on their name, we can conclude that these molecules will only contain hydrogen and carbon. Like the inorganic non-salts previously discussed, we are now dealing with covalent bonds where electrons are shared rather than given or taken like in ionic bonds. And before getting into alkanes, let's talk about the simplest hydrocarbon of all. So first I'm going to draw one carbon atom, and I'm going to show only its valence electrons as 4 dots since it has 4 electrons in the outer shell. The valence electrons are the only ones that we are concerned about when discussing bonding. Next I'm going to draw 4 hydrogen atoms around the carbon atom. Based on my periodic table, I see that each hydrogen atom is only going to have 1 valence electron. Looking at the carbon and the 4 hydrogens, I see that all 5 of these atoms have not met the duet or octet rule for stability. Carbon only has 4 electrons, but needs 8 in order to be stable according to the octet rule. Each hydrogen only has 1 electron, but needs 2 electrons in order to be stable according to the duet rule. But if I redraw these atoms where their electrons are really close to each other, I can allow them to share electrons and form covalent bonds. So let me redraw this for you guys. So I have my central carbon, I have my H on each axis, and if I draw my electrons like this, you can see that they're closer, okay? And then I've created electron pairs. So I have 4 pairs in total. So now, if I were to draw a circle all around carbon, I have 8 total electrons, and so the octet rule is satisfied. And then, if I draw a circle around each hydrogen, I see that the duet rule for each of those is satisfied. This stable molecule is going to be called methane, and it is the simplest hydrocarbon in existence. And the diagram that we have used to represent methane is known as a Lewis dot structure. To simplify this even further, though, we can turn any 2 dots into a single line. So I could actually draw methane like this, where each dash or line equals 2 electrons. So this is the more common representation of methane, and this is the basis for the remainder of our discussion today. To figure out the formula for methane, we simply count the number of carbons and hydrogens in the structure. So methane's formula is just going to be CH4. Like I said, that's going to be called methane. Alright, and if we add an additional carbon and fill the empty bonds with hydrogens, we now have ethane. So if I get rid of the hydrogen that I had on methane, the 4th hydrogen, and I add a carbon there, I fill that with my hydrogens. Now I have what's called ethane, which its formula is going to be C2H6. These two hydrocarbons are called alkanes because they only contain single carbon-to-carbon bonds. So the name for these is going to be alkanes. And the only bonds that they have is single carbon-to-carbon. So methane doesn't have any carbon-to-carbon bonds, but ethane has that one carbon-to-carbon bond, and it is a single bond because it only has 2 electrons in it. Okay. All of the names of alkanes are going to end in ane, A-N-E. And they're going to have various prefixes based on the number of carbons that they contain. And you can find these prefixes for each hydrocarbon on page 5.4 in your supplement, or in your lecture notes, or you can find it in supplement number 4. All right, so I'm going to draw out a few of these. So if I have one with 3 carbons, and each of those bonds is a single bond, and I fill it in with hydrogens on every open bond. If I look at my lecture notes, or I look in supplement 4, I see that a 3-carbon alkane is going to be called propane. Alright, and my formula for this is pretty easy. All I do is I just count my carbons. I have 3, and I count my hydrogens. H8, C3, H8. Alright, so now I'm going to draw 4 carbons. I fill all my hydrogens in. And because I have a 4-carbon hydrocarbon that only has single carbon-carbon bonds, I would call this butane. And I have 4 carbons, and I have 10 hydrogens. Alright, so let's do a few more. What if I had 6 carbons? 1, 2, 3, 4, 5, 6. And I have a little single bonds in between all those, and put all my hydrogens there. Based on my supplements and my lecture notes, I am able to call this hexane. Hex meaning 6, like hexagon. So this is going to be hexane, and I'm going to have C6, H14, and let's do one more. We'll do octane, which is going to be 8 carbons. And fill in all of my hydrogens. And I have octane. My formula is C8H18. Okay, so all of these that we've talked about, all of these alkanes, okay, so methane, ethane, propane, butane, hexane, and octane. All of these are known as saturated hydrocarbons since every available point that a hydrogen can bond, there is a carbon-hydrogen attachment. So the compound is literally saturated with hydrogens. So this is called saturated. I cannot add any more hydrogens to any of these molecules. It's kind of like a sponge that's soaked up the maximum amount of water that it can. These carbons, these carbon backbones, have as much hydrogen attached to them as they can possibly have. Okay, so that's why we refer to them as saturated. All alkanes are going to be either flammable or combustible, which essentially means that they can catch on fire. So methane, you guys might know as the primary component of natural gas, okay, which we use all over the country and really all over the world as a means to heat up our food, to heat up our homes, heat up our water, even see it now to used as different fuels, automotive fuels and whatnot. You have ethane, which is also flammable, not super commonly used as much as propane here. Propane you see all the time as an alternative to methane. You see it in North Carolina, you see it more in rural areas versus municipalities, urban areas. Butane, you can think of a butane lighter. Okay, that's what's in there. Hexane and octane, these are going to be typically found more in gasoline and different other types of fuel grades and whatnot. Okay, all of these that are listed, you've probably heard of as being flammable or combustible. Okay, basically that just means that they're going to catch on fire. All right, so we need to be very careful around these, wearing turnout gear, making sure that we're not creating any kind of sparks, anything like that. Okay. So a general formula that we can talk about with these is, at least when we're talking about straight chain alkanes, is going to be CnH2n plus 2, where N equals your number of carbons. Okay, so if I take a look back at methane, all right, I have CH4, so C1, where N equals 1, 2, 1 plus 2, so I would have C1, H2 plus 2, C1, H4, which I could just simply write as CH4. Let's try it with ethane. N equals 2, so C2, H2 times 2 plus 2, C2, H4 plus 2, and I get C2, H6. Alright, let's try it all the way down with octane. So if I have N equals 8, I could have C8, H2 times 8 plus 2, and I would end up getting C8, H18. Okay, so this is what's called a general formula. This only applies to straight chain alkanes, okay? And you'll see what I mean by straight chain here shortly, okay? That's my general formula for it. All right. So, some other prefixes that we can find related to alkanes is going to be cyclo, iso. All right, cyclo means that the alkane has a cyclical structure. Cyclical. I'll put cyclo and iso in quotations. And iso indicates that the alkane has a branched structure. All right, so if I have cyclohexane, I'm going to have 6 carbons, but they're going to be in a cyclical structure. And I can draw my hydrogens because carbon always needs 4 bonds, okay? And you guys will see that throughout this whole chapter. Carbon has to have 4 bonds. It doesn't matter how it gets them. All right. All right. So that is cyclohexane. There you go. And my formula for this is going to be C6H12, okay, which does not follow the general formula for straight chain alkanes because this is not a straight chain alkane. This is a cyclic alkane, okay? All right. My next one, talking about iso, is going to be isobutane. So but tells me that I'm going to have 4 carbons. The ane tells me it's going to be single bonds, single carbon-carbon bonds. The iso is going to tell me that it's branched. So the only way that I can draw isobutane is by branching one of the carbons up this way. And then I just fill in my hydrogens. Right? That's isobutane. Now, my formula for this is going to be C4H10, which does happen to follow the straight chain alkane general formula, but to indicate that this is isobutane, I'm going to put an I out in front of it, okay? So I have I-C4H10 indicating that this is an iso, okay? That it is branched. All right, and as mentioned previously, some of these alkanes are going to be branched, and we've referred to these as isomers. So C4H10 by itself, just regular old C4H10, which is butane, C4H10, that's our what we would call a straight chain alkane versus the branch that we just talked about. All right, that's butane. Butane and isobutane are going to be isomers, okay? And an isomer is any compound with the same formula as another compound, but with a different structure. Okay, so even though I have this little I indicator out here, because I have 4 carbons and 10 hydrogens in isobutane, and I also have 4 carbons and 10 hydrogens in butane, these are going to be referred to as isomers. Okay, an isomer is when you have same formulas or same amount of parts and different structures. We're going to see isomers quite a bit. Okay? Now, once we start finding a lot of branching, so a lot of iso-looking branching and stuff in alkanes, it's going to be easier to use a system called IUPAC when naming them. Okay? And that is called IUPAC. We are going to use IUPAC a lot in this class. Okay? So, let me draw this. So, if what we drew earlier was isobutane because it had 4 carbons, but it was branched, then we could call this isohexane because it has 6 carbons, but it's branched. Okay, so we would call this IC6H14. Okay, however, I could also have this molecule and it has 6 carbons and it's also branched, so really I could call it isohexane as well, and it's got the same formula. But my issue is I've got a carbon here that's branched off. This is called a methyl. We're going to talk about methyl later on. I've got this on carbon number 2 in this chain. If I were to name this 1, 2, 3, 4, 5, I've got it on the second carbon, whereas this one I've got it on 1, 2, 3, 4, 5. I've got it on the third carbon. Okay, so these are not the same molecule. Okay, however, we can use a different type of naming scheme for these, all right, in order to differentiate between the two, because these are 2 distinct molecules. These are going to have slightly different properties. They're going to behave similarly, but they're still going to have slightly different properties, and we have to treat them as such. We have to treat them as unique compounds. Okay, so we're going to use the IUPAC naming scheme in order to properly name these. So to use the IUPAC naming scheme, first we're going to start with the longest continuous chain of carbon atoms in the molecule, which is the main chain. So for this one, my yellow one, isohexane, I've already drawn it out. This is my largest chain. 1, 2, 3, 4, 5. 5 carbons in a straight chain. This is going to be, let's see, I'll draw it up here. This is going to be called pentane, right? 1, 2, 3, 4, 5. That's going to be pentane. Okay? So, next, I assign numbers to the carbons, counting from the end that will give the groups attached to the chain the smallest number. So, I've already done that. 1, 2, 3, 4, 5. I wouldn't go 1, 2, 3, 4, 5 because 2 is going to be less than 4. Here, I'll draw that out for you. So, if I were to go 1, 2, 3, 4, 5, all right, the 2 here, 2 is less than 4, so I go with my 2, all right? So 2's the winner whenever I'm naming this, all right? So this methyl group that's attached to the main chain, all right, my CH3, okay, that's what we refer to it as, is methyl. So we can call this first molecule 2-methylpentane, 2-methylpentane, because I have my methyl group on the second carbon of a 5-carbon chain. So that is going to be my IUPAC name for this. And I can do the same thing down here, where I start with my longest chain, and again it's going to be pentane. I count my carbons, 1, 2, 3, 4, 5. I could go the opposite way, and because this is symmetrical, it's not really going to matter, okay? But I have my methyl coming off of my third carbon, so I can call this 3-methylpentane. So instead of having both of these called isohexane, which is kind of confusing, now I can name the one 2-methylpentane and the other 3-methylpentane. Okay? Let's go to some more examples. Alright, so gonna draw my hydrogens, and we'll add some carbons coming off of there. Oops, there we go. And we'll put some hydrogens on these carbons just because we have to make this saturated. Alright, so how in the world do I name this thing? Okay, so first things first, I find my longest continuous chain, okay, which it looks like if I start here and go all the way here, okay, then that's going to be my longest chain. So 1, 2, 3, 4, 5. So I've got 5 carbons, so I'm going to go ahead and label that as pentane as my longest chain. Okay? I could also try going the other way as far as my numbering goes. 1, 2, 3, 4, 5. And I still get pentane, but 2 is going to be less than 4 whenever I'm naming these methyl groups coming off. Alright, so the 2 wins. So I'm going to go with the 2. Alright, so I've got a methyl group here, and I've got a methyl group here. So I've got 2 of them. So in a case like this, I'm going to use the prefix di to indicate that there are repeating substituents. That's what the name of the methyl groups are, the general name. They're going to be called substituents or groups, okay? So this is called a substituent. In particular, it is a methyl group, okay? And because I have 2 of them, I can call this dimethylpentane. Now, I still have to be specific about where these are, because I could have one methyl group here, but I could also have one over on the third carbon. But because I've got both of them here, okay, I'm gonna call this 2, 2 dash dimethylpentane. Okay, I indicate where both of my methyl groups are by numbering them. Okay, I wouldn't just say 2 dimethylpentane. I would say 2, 2 dimethylpentane. Okay, I'm designating the location by the number of the carbon atom to which they are attached. And because both of these are attached to the second carbon in that chain, I have to indicate that number. Okay, that's IUPAC rules. Let me show you guys. Sorry. 2, 2-dimethylpentane. All right, and my formula for this, all I would do is I would just count. Okay, so my formula is going to be C7, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, which just so happens to follow my general formula for straight chain alkanes. Okay, C7H16, 2,2-dimethylpentane. All right, there's not really an easy common name to name this, like iso heptane or anything like that. It's easiest just to do 2,2-dimethylpentane. That was one of the reasons IUPAC adopted this naming scheme. Okay, let's go on to another one. So if I have, let's do a 6-carbon parent chain, and let's do you guys are probably thinking, what the heck is this thing? But trust me, you will see some very gnarly looking molecules by the end of this class. Alright, so how in the world do I name this thing? So what I do is I find my longest continuous chain. Okay, so 1, 2, 3, 4, 5, 6. So that's going to be hexane. Hexane. Okay, so I number these. I number these carbons. 1, 2, 3, 4, 5, 6. Okay, and I'll number them the other way as well. 1, 2, 3, 4, 5, 6. Now, what I'm trying to do is I am trying to figure out what is the lowest, or which configuration will give me the lowest numbers. Okay, so if I find my methyl groups, which are here, here, and here, all right, if I go in the direction from left to right following the red, I would have 3, 4, 5 trimethyl. 3, 4, 5 trimethyl. Oops, didn't give myself enough space. Or if I went the opposite way, okay, I would have 2, 3, 4 trimethyl. 2, 3, 4 trimethyl hexane. Now, IUPAC says I go with the lowest numbers, okay? The orientation or the direction that gives me the lowest numbers. So, this is going to be my winning name, okay? 2, 3, 4 trimethyl hexane, because the opposite direction gives me 3, 4, 5. I always go with my lowest numbers. Okay? And because I have 9 carbons in total, and every one of them is saturated, my formula for this is going to be C9H20. Okay? And notice that in every example that we've discussed so far, all of the carbons always have 4 total bonds in order to satisfy the octet rule, since each bond is 2 electrons. Okay, so every single one of these examples that we've talked about up to this point, the carbon always has 8 electrons all around it, okay, which since 2 electrons equals 1 bond, it means it has 4 bonds, so 4 different lines around every single carbon. All right, seriously, you can go back, look at the video, see that every single carbon is going to have 4 bonds attached to it in some way. Okay? Alright, I adjusted my zoom on my tablet so you guys should be able to see this a little better without me having to scroll. So we're going to talk about alkenes, which, there we go, alkenes. And these are going to contain at least one carbon-to-carbon double bond. So alkanes, we're all about single bonds, whereas these are going to be carbon-to-carbon double bonds. Alright, and these are going to be named with the same prefixes as the alkane, so meth, eth, prop, but, pent, etc. But these are going to end with ene instead of ane. And like the alkanes, these are also going to be flammable. Okay, that's going to be one of their primary hazards. Alright, so let's draw ethene. Okay, ethene, I have 2 carbons. Alright, and if I do a double bond between them, alright, a carbon-carbon double bond, now, like I've said previously, carbon always has to have 4 bonds. Okay, so if I add hydrogen to it, I look at my carbons, I can circle them, and I see I've got 2, 4, 6, 8 electrons. And if I go around this one, I see I've got 2, 4, 6, 8 electrons around that. So this is happy. And I can call this ethene. And the old school name for it is ethylene. Okay, notice that ethene indicates that it is the carbon-carbon double bond. Okay, so a 3-carbon one, 1, 2, 3, and I'll put my double bond there. Okay, and I'll have a single bond there, so I'll just fill it in with hydrogens. This one's only going to have 2 hydrogens, right? Because I've got two double bonds attached to this. Because this carbon has 1, 2, 3 bonds already, I'm only going to put 1 hydrogen on it. And because this carbon only has 1 bond, I'll put 3 hydrogens on it. Okay? And you can go through these, circle the carbons, and make sure that the octet rule is satisfied. Okay? This molecule is going to be called propene because it's got 3 carbons and it's got a double bond in it, or you'll see it as propylene. Okay? That's a classic name for it. Alright? And these hydrocarbons, your alkenes, are going to be considered unsaturated because they do not contain the maximum number of hydrogen atoms possible for the number of carbon atoms present. So remember, my alkanes were saturated because they had as many hydrogens as they could possibly have. Okay, so if I look at propane, propane had 3 hydrogens here, 2 hydrogens here, and another 3 here, whereas propene, I've got only 2 hydrogens here, only 1 hydrogen here, and then this is the only carbon that actually has 3 hydrogens. Okay, so we would call alkenes unsaturated. Unsaturated. Alright, my general formula for alkenes is going to be CnH2n. Alright, and again, where n equals my number of carbons. So if I come back up here to ethene or ethylene, I have C2H2 times 2, and I end up with C2H4. And with propene, I have C3H2 times 3, and I get C3H6. Okay? Alright, now if more than one double bond is present, and here's an example of that. So if I have 4 carbons, and let's put a double bond there, let's also put a double bond there, put a single bond there, and let's fill it in with hydrogens as it will allow us to. And you can check the octet rule for all of these. So if I have more than one double bond, it is called polyunsaturated. That's not the IUPAC name, that's just the classification of this, like saturated or unsaturated. Polyunsaturated. And it's going to have the suffix diene, okay? Di meaning two, and ene meaning double bonds, carbon-carbon double bonds, which makes sense. I've got 2 double bonds in here. I've got one there, and I've got one there. So a name that we can call this is going to be butadiene. Okay, because I've got 4 carbons, that's the buta part. I've got double bonds, that's the ene part. And in fact, I've got 2 different sets of double bonds, so that's the di part, as butadiene. Alright, and my formula for this is going to be C4H6, which notice this does not line up with the general formula for alkenes. Okay, the general formula for alkenes is only going to apply to alkenes that are straight chain and have one double bond in their structure. Okay. All right. So let's get back to just regular old alkenes instead of dienes. So we also have to be concerned about the location of the double bond with some of the larger alkenes. Okay, so if I have another 4 carbon alkene, and I'm not going to do dienes, I'm just going to do one double bond. So if I have this, and oops, let me get rid of that, I got carried away. Alright, filling in my hydrogens. Alright, and we'll go ahead and put my formula out. It's going to be C4H8. Alright, so let me draw an isomer of this, which remember, an isomer is something that has the same formula but a different structure. So I'm drawing my isomer, which is also C4H8. All right, you can see that these 2 molecules are different. Okay, they are isomers because they have the same formula, but they have different structures since the double bond is at different places in each molecule. Okay, I have the double bond here bridging this first carbon and the second carbon, so 1, 2, 3, 4. So I have that double bond bridging the first carbon and the second carbon in this molecule, but in this one I have it bridging carbons 2 and 3. Okay, so to name these, we're going to find the smallest numbered carbon that contains a double bond. So for this top one, it's going to be 1. Okay, that's the smallest number. Between 1 and 2, 1 is less than 2. And with this one, we have 2 and 3. Because 2 is smaller than 3, We're going to circle this. So for the first molecule, we're going to call it 1-butene. Okay? My ene indicates that there's a double bond somewhere in there. My bute indicates that there are 4 total carbons, but my 1 indicates that that double bond, that carbon-carbon double bond, bridges the first carbon and the second carbon. I can also see this written as bute 1-ene. Okay? Either one works. Alright? This one, by the same logic, I can name it 2-butene. Okay? Because my double bond bridges the gap between my second carbon and my third carbon. Or I could call this bute 2-ene. Okay? So you can see that these are isomers. Alright? Same formula. Alright? Same formula over here. Different structures. And so I have to be specific about how I name them. If I just name this top one butene, I'm incorrect. I'm partially incorrect. Okay? Which partially incorrect on a hazmat scene can be all the difference sometimes. So you want to be as descriptive as you can. Okay? Descriptive and specific. So 1-butene is correct. 2-butene is correct for the bottom one. Okay? So when you're working out problems and stuff like that, be specific. Be as specific as you can. Okay? Now, the single, just to go over this portion, the single carbon-carbon bond in an alkane is called a sigma bond. Okay? And we can actually draw these right here. So that bond right there is called a sigma bond. Okay? And that bond right there we can also call a sigma bond. Okay? Now, this second bond here, we're going to call it a pi bond. So all alkanes have sigma bonds. And really all alkenes do too. Okay? But only alkenes and alkynes, which is what we're going to talk about next, have pi bonds. Okay? And alkenes, that double bond has a sigma plus a pi bond. Alright? And pi bonds in general are much less stable than sigma bonds. Okay? So all you need to know, and we're not going to get too terribly deep into why, but pi bonds are unstable. Okay? So, because pi bonds are much less stable than sigma bonds, any molecule containing a double bond will be highly reactive. Okay? So, alkenes are going to be highly reactive, in addition to being flammable. Okay? In particular, these highly reactive pi bonds can lead to a process called polymerization. You may have heard of this. Okay? Polymerization. So, polymerization is typically used in a controlled process, and you'll see it a lot in the production of plastics and various other common products. A lot of stuff you'll probably see in a landfill that you should have seen in a recycling bin, but I digress. Uncontrolled polymerization is what we may encounter on a hazmat incident, and it can ultimately lead to an explosion, okay, or a catastrophic event. So alkenes have the additional hazard of being able to potentially polymerize. Okay, so supplement number 11 in your workbook, that is going to expand upon the hazards and the science behind polymerization. Okay, it is something that I harp on a lot because polymerization is the only hazard where I can look at a chemical and uh, be able to assess that it is going to have a polymerization hazard. Okay, all because anything with a double bond, okay, that extra pi bond is able to polymerize. So everything that we've talked about so far. So ethylene, ethene, okay, if I have that double bond there, okay, and for whatever reason it starts to polymerize, now I'm going to have what's called polyethylene as this starts to link up with each other, okay? Here, I'll draw it out for you guys. So, polymerization. Polymerization is if I have multiple ethylene molecules, and I'm just going to draw in my hydrogens. So, if I have a polymerization reaction, essentially what happens is that pi bond, that really unstable pi bond, the second group of electrons in my double bond, okay? Remember, I said that my sigma bond is pretty stable, whereas my pi bond is unstable. Essentially what happens, okay, is I add heat or I get rid of what's called my inhibitor in my container, okay, and you can learn more about this in supplement 11. But essentially what happens is this bond breaks and it comes here, okay? This one breaks and it comes here like a chain reaction. Oops. And what you ultimately get is you get a new chain of molecules and I'll show you what those new bonds look like. So those new bonds are there and there and there. So now essentially I've taken these small molecules, okay, that are able to move past each other and stuff like in a vapor, and now I've tied them together by polymerizing them. And so my volume of that chemical, okay, because this was ethylene and now I have polyethylene, that volume is going to increase against the walls of that container, and that's how I'm able to get expansion of that container and ultimately an explosion, catastrophic event, okay, catastrophic release of this stuff. All right, so if I do have something that does have a double bond in it, like butadiene or 1-butene or propylene or anything like that, if I have anything that has a container that's anything like that that is in a container, I need to be monitoring my temperature of that container, okay? Because with temperature, you can get that polymerization, okay? And you do not want to be dealing with this stuff. Imagine an explosion, so you're going to get a bunch of energy and fire because this stuff is flammable, but you're also going to get raining globs of plastic, okay? Super duper hot plastic from where this ethylene has turned into polyethylene, okay? So, I digress. As with the alkenes, all right, so back to just regular old alkenes, not talking about polymerization anymore. Note that each carbon is going to have 4 total bonds to satisfy the octet rule, okay, with some being single and others being double. So if we look at butene here, notice that this carbon has 4 bonds, okay, which means that it has reached the octet rule. This one has 4 bonds, octet rule, 4 bonds, octet rule, 4 bonds, octet rule. Doesn't matter how it got them, okay, but it has 4 bonds, so it has met the octet rule since each bond consist of 2 electrons. Okay? Alright, so the next group we're going to talk about is the alkynes, and these are going to contain a triple carbon-carbon bond. So these are called the alkynes. They're going to contain triple bonds. And this is a pretty small family. There's only 2 examples that we're going to talk about because these are very unstable, and we're going to talk about why. The only one for us that is of major interest is going to be ethyne, and that's going to be called ethyne, and it is going to be 2 carbons based on the eth portion, and I've got that triple bond based on the YNE portion. Okay, alkynes are going to have YNE as their suffix, and I'm going to attach 1 carbon on either side just to make the carbons happy, and that's a relative term because this is a very unstable molecule. You may have heard of it called acetylene. Okay, acetylene, that's the old school name for it. Okay, and due to the presence of yet another pi bond, so we have 1 pi bond there, 1 pi bond there, pi bonds, and the one in the middle we can call a sigma bond. Okay, because we have 2 pi bonds in here, these are going to be extremely reactive. So where alkenes were highly reactive, these are going to be extremely reactive. Okay, and very unstable. Alright, acetylene, we haven't really talked about flammable range yet, okay, but we will in chapter 7. Alright, flammable range for acetylene is going to be about 3% to 100%. Okay, for reference, methane's is just 5% to 15%. And what that means is basically with methane, if I have 5% methane in air, or if I have 5% methane in air all the way up to 15% in air, and I were to light a match, I'd be able to blow up that room. Essentially, it would ignite all of that gas. Okay, but anything below 5% or anything above 15%, it's going to be either too lean or too rich. Where something like acetylene, which is extremely reactive, it doesn't have an upper limit. You cannot be too rich with acetylene, and 3% is pretty dang low. So essentially, anytime you have acetylene, it has the potential to ignite. Okay, so it is very dangerous to be around. All right. So all alkynes are named with the same prefixes as alkanes and alkenes, but like I said earlier, they're going to end in "ine." So we have that F there. Acetylene's just the old school name for it. We'll do one more example. So let's do propyne, which the prop should tell you I'm going to have 3 carbons, and the ine should tell you one of these is going to have a triple bond. So we'll just say that it's this one. So I add a hydrogen there, and to make this bond here, this carbon's not going to have any hydrogens on it at all, whereas this one is over here hanging out. It can have 3 hydrogens. Okay, so my general formula for by the way, we can also call this methyl acetylene. My general formula for alkenes is going to be CnH2n minus 2. So I can come back here to acetylene, and I've got 2 carbons, and I've got 2 hydrogens, minus 2, C2H4 minus 2, and that's going to give me C2H2, which sure enough is what I have. Down here I've got C3H3 3 minus 2, oops, 2 times 3 minus 2, so that's going to be C3H6 minus 2, C3H4. Okay, and again, notice with my alkynes, all right, that each carbon is going to have 4 total bonds to satisfy the octet rule, whether those be single bonds or double bonds or triple bonds or bonds to hydrogen, doesn't matter. If there's a carbon, it is going to have 4 total bonds. Okay. Next we're going to talk about aromatic compounds, and these are hydrocarbons that contain a benzene ring. All right. So benzene is going to look like this. Very similar to cyclohexane, but you will see the difference. And we've got little bonds here, here, and here. All right, so that's benzene. All right, but the thing is that these double bonds, they're passed around. Okay, so kind of how I drew for the polymerization, where the bonds are moving around and whatnot. These bonds are moving around too. And so I end up with another form of benzene where my double bonds have moved. And these keep on kind of rotating around too. Just around and around they go. And so this is called resonance, where my electrons are basically passed around. And so what I can do is draw a configuration of this that makes a little bit more sense now that we know about resonance. I can draw a circle in there. And going even further, I may see benzene written like that. Okay? And when it's written like that, you can assume that all of these points here are carbons with hydrogens coming off of them. So kind of like that. That's what those are. All right? That is my benzene ring. Okay? And like I discussed up here, my resonance or resonant bonding, all right, is essentially where those electrons are being passed around, okay, back and forth and back and forth, okay. This type of bonding, believe it or not, is the most stable type of bonding we're going to find in hydrocarbons, because these electrons are shared across the entire molecule rather than being localized between carbons. All right, so aromatics in general are going to be very stable chemically, but many of them are toxic, with benzene actually being a known carcinogen, which we all know what that does. That is cancer. And aromatics are also going to be flammable. Okay? Now, that's benzene, and my formula, just counting my carbons and my hydrogens, is going to be C6H6. Okay. So I have another molecule. My next molecule is going to be called toluene. Okay, and all it is a benzene molecule. So we'll do my 6 carbons, and I'll draw my little resonance circle. But benzene is going to have a methyl group in place of one of the hydrogens. So I'll draw my hydrogens. So this is going to be a methyl group. Right there. CH3, my methyl group. Okay, so I can also call this methyl benzene because I have that methyl attached to a benzene. Makes sense. Alright, my formula for this, I can count all my carbons, count all my hydrogens, is going to be C7H8, but how I prefer to do it is, so if benzene, right, benzene was C6H6, but if I get rid of one of those hydrogens and turn it into 5, now I've got this whole group right here. So instead I could name this C6H5, and then I add this on the end of it, CH3. Okay, that's another name, another way that I can write my formula out. To be honest, I prefer this way to write the formula because it's descriptive. C7H8 really doesn't tell me a whole bunch, but C6H5, okay, I can kind of see that, and I can think, huh, that reminds me awfully like a benzene ring, okay, awfully of a benzene ring, but I've taken off one of the hydrogens and I've replaced it with a methyl group, which sure enough I have, okay. And like benzene, this is also going to be flammable and toxic. This is a suggested carcinogen. They think it may be cancer causing. They're not sure. I would err on the side of caution. Okay. Xylene is going to be our next molecule we're going to talk about. And it is going to be a benzene ring with 2 different methyl groups in place of 2 of the hydrogens. Okay. So we'll do good old benzene with my resonance ring there. Put some hydrogens. And we'll do some methyl groups. Okay. Now, the thing with xylene, because I've got 2 methyl groups, I have 3 different isomers that I can have. Alright, so I'm going to draw another one. And now you'll see that my methyl group is in a different spot. Or at least one of my methyl groups is in a different spot. And if I go even further, I can have that 3rd isomer. You can probably see where this one's going to go. Put all my hydrogens in there. Okay, so these are my 3 isomers. Okay. Alright, so the first one is going to be called orthoxylene. Orthoxylene, or I could call it, here, let me get rid of this, give me a little bit of space to work. I could also call this O-xylene. Alright, I could also call it 1,2-xylene because I've got a methyl on my first carbon, I've got a methyl on my second carbon, or I could call this 1,2-dimethyl benzene. Okay, either one of those. All right, orthoxylene, O-xylene, 1,2-xylene, or 1,2-dimethylbenzene. Since I have a benzene ring with two methyls, one in the coming off of the first carbon and one coming off of the second carbon. All right, and I will draw this one in blue for you guys. So this one here, this one is going to be meta-xylene, or I can call it M-xylene, or I could call it 1,3-xylene. Even further, I can call it 1,3-dimethylbenzene. Okay, because my carbons are 1 and 3 that have the methyl groups coming off of them. Okay, and finally, my last isomer, I'm going to call this para-xylene. Alright, and this is just something that IUPAC has came up with. Okay, this is not Tyler's names for these. These are the names that we have to know. Could also call this 1,4-xylene, or you've probably guessed it, 1,4-dimethylbenzene. Okay, because I have the methyl coming off of that first carbon and the fourth carbon. Alright, and because these have the same parts, okay, same formula, but different structures, these are going to be called isomers. And in particular, their formulas are going to be C8H10, which kind of like with toluene, I'm not a big fan of this, so what I can do is do C6H4, and because I've got two methyl groups, I'm going to put that methyl in parentheses with a 2 out there. And if I have, say, ortho, I could put an O out there, or if I have meta, I can put an M, or if I have para, I can put a P out there, okay, in front of that formula. So, say 1,4-dimethylbenzene would be PC6H4CH3, all in parentheses 2. Now my general formula for my aromatics, aromatics is going to be CnH2n minus 6, where N is my number of carbons. Alright, so for benzene, 6 carbons. So H2 and, oops, go ahead and draw that in. 6 minus 6, C6, H12 minus 6, C6, H6, which is what I had on my previous screen. Alright, toluene. It's going to be C7, H2, 7 minus 6, C7, H14 minus 6, and I get C7, H8, and then xylene, all three of my isomers, it's going to be C8, since I have 8 carbons, 6 for the benzene ring, 2 for each methyl. H2 times 8 minus 6, C8, H16 minus 6, and I get C8, H10. Okay, that's my general formula. Now, like I've said previously, I'm a big fan of elaborating on these. Okay, so xylene, I would really have C6, H4, CH3, all in parentheses with a 2 out there. Okay, but your general formula at least tells you how many parts you're going to have. Okay. Now we're going to talk about something called radicals. So first, let's consider methane. Good old simple alkane methane. All right. If we remove one hydrogen from methane, so let's get rid of this one, we now have what's called methyl, which we've seen a little bit of already. Okay, we can also call this CH3 with a dash out there, and all that dash is indicating is that we have this open bond right there. Okay, methyl is an example of a hydrocarbon radical or backbone. Okay, so you can also see this generally called a backbone or radical. All right, and the only reason it's called a radical or a backbone is because we can now add something other than hydrogen at that open bond. Okay, so I can put something here instead of hydrogen. All right, we're going to talk about that here in a little bit. All right, but first I'm going to show you the next radical we're going to talk about. So if I have, let's say, ethane, C2H6, all right, and if I remove a hydrogen, now I have ethyl. Okay, so just like methyl, I got rid of a hydrogen, now I have ethyl. All right, and I can write this out as C2H5 with a dash, or I could do CH3, CH2 with a dash. Okay, and that dash just corresponding to my open bond that I have now. All right, so we could use this same naming logic for all of the other alkanes, where we're going to maintain the prefix but change ane into -il when we remove the hydrogen. Okay, so notice, back up to methyl, we went from methane to methyl. Down here we went from ethane to ethyl. Okay, now The naming of alkene radicals is going to be a bit different. Okay, so let's consider ethene. Okay, so I've got my two carbons. All right, and since it is ethene, I've got a double bond. So I'm going to fill in the gaps with my hydrogens. All right, so if I take off one hydrogen from ethene, let's take this one off, we now have a radical that is called vinyl. Okay, and this is going to be tough to remember, but you guys are going to be able to use your supplements on your final exam and whatnot, so don't worry too much about it. And the radical, or excuse me, the formula is going to be C2H3 with a dash, just because I've got two carbons and three hydrogens. Okay, so I know that this can be a little bit confusing, but this is a naming scheme that is used instead of ethenyl, so it isn't misunderstood to be ethyl. Okay, so ethenyl sounds a lot like ethyl, okay, especially when you're trying to describe what's written on a container by using a radio. Okay, so it's easier for me to say vinyl when I'm talking about something based on ethene versus ethenyl, where it could be confused for ethyl. All right, so another example is going to be propene. And I've got my hydrogens. And if I get rid of one of the hydrogens from propene, in particular on the side that is the fully saturated side over here, get rid of that one. Now I have what's called acryl. Okay, and my formula for this is going to be C3H5 with a dash. Okay, you could also potentially see it as CH2, CH, CH2 with a dash, but most of the time you're going to see it as that one, C3H5. Okay, again, this is used instead of propenyl, so it isn't misunderstood to be propyl. Okay, and finally, we have one that is derived from 2-butene. So 2-butene, not to be confused with 1-butene. And so if I remove a hydrogen from this one, now I have the name crotyl. Alright, and like I said, these are on the supplements. I know that these are not the easiest names to remember. And C4H7 is going to be my formula for that. Okay, now concerning aromatic radicals or backbones. Okay, so let me draw a benzene ring. And I've got all my hydrogens. And I've got my little resonance ring there. So if I were to remove a hydrogen from this, now I am going to have what's called phenol. Okay, and my formula for that is going to be C6H5 with a dash. Okay, and that dash is just going to, like the other ones, correspond to that open bond. Alright, and if I draw toluene, and I'm going to have my methyl out to this side. So I have toluene, and if I erase the hydrogen on the methyl group, okay, now, and this is where it's confusing, now this is called benzyl. And my formula for that is going to be C7H7 with a dash, or more specifically, I could say C6H5CH2 with a dash. And I know what you're thinking, okay? It doesn't really make sense that I take a benzene ring and I knock off a hydrogen off of it and it turns into phenyl, but then I have toluene, knock off a hydrogen from it, and now I have benzyl. I get it. I do not make the rules. I only teach it and I follow them, okay? So now you may be wondering what we do with that open bond on all of the radicals that we've created. If our hydrocarbons were only limited to the alkanes, alkenes, alkynes, and aromatics, we would only have a few dozen known chemicals in organic chemistry. But the thing with organic chemistry is it encompasses millions of different chemicals because we add things called functional groups to our hydrocarbon radicals or backbones. And these functional groups added to a hydrocarbon radical are going to create something called a hydrocarbon derivative. Okay, so my name for these is going to be hydrocarbon derivatives. And these hydrocarbon derivatives are going to have properties that are going to differ drastically from the original hydrocarbons. Okay, so an example of this, let's start out with good old methane. All right, and if I remove a hydrogen, all right, and if I add NO2 to that open bond, NO2, that's called a nitro group. We now have a chemical called nitromethane. Okay, methane, which is the primary component of natural gas, okay, is not toxic, but it is flammable, and it's used for heating and cooking all over the world on a daily basis. Okay, chances are you have natural gas either in your house or at the fire station or in plenty of the buildings that you go into, and you don't even think about it. Okay, nitromethane, on the other hand, is a toxic liquid with explosive properties that is used as a racing fuel additive. So as you can see, the functional group, which is the nitro here, it changed the function of the original hydrocarbon. Okay, it changed the function. So this guy here is called a functional group. Functional group. And the thing that I attached it to here is called my radical or backbone. Either one works. Okay? The general formula for hydrocarbon derivatives utilizes R for the hydrocarbon radical or backbone. So this portion is going to be R with my dash, and then the functional group can be used to complete the derivative. I should say. For instance, the general formula for nitro compounds like nitromethane would be RNO2. So this is going to be RNO2 because that's my functional group. All right. If we have a hydrocarbon derivative that has multiple hydrocarbon radicals, like an ether, we can call the second hydrocarbon radical R prime. Okay, so ethers, my general formula for ethers is going to be R dash O, and then I'm going to have another radical over here, but R prime, okay, which means that it can be different, okay? So that and that are not necessarily equal. They can be, okay, but they're not necessarily equal. And we will see those quite a bit in chapter 6, okay? So we can also have radicals that are made from isomers, which is primarily seen with butyl isomers, okay? Butyl isomers. This is something we're going to talk about because you will see it in your practice problems and homework, okay? So let's draw OH, and let's do some butyl isomers. So butyl means 4, so each of these is going to have 4 carbons on it. And let me draw this one over here. We'll do red. Draw my hydrogens. And let's do one more. So notice that all of these hydrogen backbones have only 4 carbons, hence them being referred to as butyl isomers. Okay, they have the same number of carbons, same number of hydrogens. Oops, I forgot one over here. Same number of hydrogens, all right, same number of oxygens. Each one has an oxygen atom in it. Okay, so these are isomers, and in particular, because they have 4 carbons, they're butyl isomers. And to figure out the name of each isomer, we're going to look at the carbon directly attached to the functional group. Okay, and these can be rather tricky to name, so I'm going to walk you through how to do it. Okay, so first things first. All right, we look at the carbon directly attached to the functional group. So I'm going to look at that one for this first example. Okay, if that carbon is attached to only one carbon, which indeed it is, all right, that is the only carbon that is attached to that initial carbon. Okay, if you only have one, we are going to call it isobutyl. This radical is isobutyl. Okay, and because I have that OH there, this is going to be isobutyl alcohol, where my isobutyl is my radical. Oops, I was almost going to spell alcohol. Alcohol. All right. So if the carbon attached to the functional group is attached to 2 carbons, so this one is attached to 1 carbon, 2 carbon, we're going to call this secondary or sec butyl. And since I have that OH there, we're going to call it sec butyl alcohol. We will talk more about alcohols in chapter 6. For right now, focus on the butyl portion of this. Okay? And this one, I have my initial carbon there. Alright, and if the carbon attached to the functional group is also attached to 3 carbons, 1, 2, 3, I'm going to call this tert butyl alcohol. Okay, so in this case, iso means 1. Okay, isobutyl alcohol. That first carbon is only attached to 1 carbon and then it branches. All right, sec, in this case sec or secondary means that I am attached to 2 different carbons, the first and the second. And then tertiary butyl in this case means 3, which means that this initial carbon is attached to 3 different carbons. Okay, so note that this only applies to the butyl isomers. Okay, and a summary of these rules can be found in supplement number 5. Okay, and I promise that you will get plenty of practice with the butyl isomers throughout chapter 6. Okay, so that's all I have for chapter 5. A good summary of hydrocarbons is on the top portion of supplement number 4. And as always, contact me if you have any questions. I'll see you guys when we tackle chapter 6.